Okay, let's get started. Welcome. Very happy to have Professor Phil Armitage here from CU. Phil is a professor at the CU's Department of Astrophysical and Planetary Sciences department, and also he's a Gila Fellow. He received his undergraduate and graduate degrees from Cambridge University, and he did this postdoc research at the Canadian Institute for Theoretical Astrophysics at the University of Toronto, and then the Max Planck Institute on Astrophysics. And he joined CU in 2002. His research interests include planet formation, accretion disks, and computational astrophysics. Phil is also an excellent photographer. On his website, I saw some really, truly amazing pictures. And but today he's going to discuss the role of turbulence in planet formation. Phil?
Amazing turbulence. Yes. Thank you. So what I'd like to talk about is some of the work we've been doing on trying to understand the properties of turbulence in protoplanetary disks, which are the environment for planet formation, and say a little bit perhaps about what some of the implications of that turbulence might be for different aspects of the planet formation process. So to just set the stage here, we know that the environment of planet formation is protoplanetary disks around young stars, and both in the optical and the infrared, and also in submillimeter measurements, we now have sort of limited but reasonably good observations of those systems. So what you're seeing on the right there is a protoplanetary disk of a particular star. It's a relatively nearby star to the Sun, imaged with the Hubble Space Telescope. The star is in the center there, blocked out, and this is almost a face-on disk with a scale that is somewhat comparable, roughly comparable, to the scale of the solar system. And here you can see, there's some apparent structure here, which is mostly noise in the image, but maybe if you sort of squint, you can see there's sort of a dark band here, which probably does represent genuine structure in that disk, whose origin, in fact, is not understood. So we have some observations of these systems and some inferences. Sorry.
I'm wondering what stage of the parent star
Yeah, so this particular disk is maybe about 10 million years old, and so it's the star is just reaching the main sequence, and that would obviously depend a little bit on the stellar mass. So the disk lifetime is roughly comparable to the pre-main sequence. The pre-main sequence stage of stellar evolution.
The star is how massive?
The star is a little bit less massive than the Sun. So these disks, when we can observe them, have scales that are roughly comparable to the solar system of order 100 AU. We believe they have lifetimes, median lifetimes of maybe in the range of 5 to 10 million years. And that means that they're approximately equilibrium structures in Keplerian rotation. They live for, obviously at small scales, for many millions of orbital times. So they must be in very good equilibrium with rotation balancing gravity. Of course, they're not completely in equilibrium. There's some slow inflow, which leads to mass being accreted by the star, and presumably at earlier stages, which become somewhat harder to observe, there must have been more rapid inflow to actually form the star and give the star most of its mass in the first place. In terms of physical conditions, the temperature obviously depends where we are in the disk. Close to the star, it will be somewhat comparable to stellar photospheric temperatures, maybe reaching 1,000 degrees, or even a little bit hotter than that. If we go maybe to large scales, 100 AU, you'll be approaching the background temperature in star formation regions, and so you'll be looking at more like 10 Kelvin. The densities are rather low, so at 1 AU, an estimate for the mid-plane density might be 10 to the minus 9 grams per cubic centimeter, and most of this mass is gas, so it's primarily hydrogen and helium, and roughly speaking, we expect that there's something like 1% of the total mass is in the form of condensable materials, which in close to the star, those would be rocky materials, things like silicates. If we go further out, beyond maybe 3 or 5 AU, the dominant material would be icy material, predominantly water ice. So that's the environment in which we think planets are forming. Now, why are we interested in turbulence in planet formation? Well, if we're just interested in the overall structure of the disk, we actually have some pretty good constraints now on what that structure looks like, at least on relatively large scales. So if you ask, well, what is the structure of planet-forming disks at 1 AU? So if you're mostly interested in the formation of the Earth and the terrestrial planets, then observations on those scales are still extremely challenging. However, on larger scales, we have quite good observations. Here's an example from some fairly recent work by Sean Andrews and collaborators. This is a map made in the radio in millimeter wavelengths. The contours here are showing the intensity of this submillimeter emission. And then the colors here are showing the Doppler shift of molecular lines observed in that system. So here's another disk that is in fact almost face-on. You can see it's not quite face-on. Over here we have red-shifted emission, here blue-shifted emission. This disk is actually slightly tilted to our line of sight. So we have quite good constraints on, say, what the density and maybe even the radial dependence of the density and the temperature and so forth look like, at least on fairly large scales. However, if we're interested in planet formation, we're also very interested in the turbulent properties of the fluid, because that will clearly stir up what's initially very small particles, micron-sized dust particles, and affect how they collide. So this is rather critical, but this is much harder to measure directly. So what we've been trying to do is sort of a three-stage approach. We've been trying to model the properties of turbulence in these rotating disk systems as a function of the distance from the star. We're then trying to constrain those theoretical calculations with observations. And then ultimately, we'd like, of course, to study the implications that that has for different aspects of the planet formation process. And I think it's easy to convince yourself that turbulence ought to be important. As we'll see later, both the theoretical and the available observational information suggests that the turbulent motions are maybe a tenth or a few tenths of the sound speed in these disk fluids. So, you know, this corresponds to very, very violent turbulence if you sort of compare it to terrestrial environments. Exactly. So this maybe is not good for, you know, maybe this would be ripping things apart rather than bringing them together. So this is how I'm going to structure the talk here. I'm going to begin with a little discussion of the different ways in which turbulence is thought to be important in these systems. What do we know about it? How can we model it? Show some results, and then discuss some ongoing work to provide better observational constraints that we can compare with theory. So this is work that's being done with a large number of collaborators. The main person working on this is Jake Simon, who's at Southwest Research Institute here in Boulder. And then we're working with some collaborators in Harvard and Princeton. And Meredith Hughes in Wesleyan is leading the observational part that I'll just touch on at the end. So the turbulence can, of course, have different roles in protoplanetary disks. And there are maybe sort of three areas, independent areas to some degree, where we're interested in how turbulence might affect different parts of the planet formation process. So one of them, which is, I would say, from the astrophysical side, the sort of motivating driver for much of this work, is to understand how angular momentum can be lost from this disk in near Keplerian rotation, so that the gas can actually lose angular momentum and flow onto the star and be accreted. And this is tied up with the question of how long protoplanetary disks live. Is that 5 or 10 million year lifetime the time it takes for the angular momentum to be lost, or at least transported within the fluid, and the gas to accrete? Or is it instead reflecting how long that gas can survive before it's blown away, for example, by thermal winds produced by X-rays that are impinging on the surface of the disk? So we're interested in it from the point of view of the disk lifetime, and then there's a related question, which is that how the angular momentum is transported in the disk turns out to affect the migration rate of low-mass planets and giant planet cores that form within the disk. So depending on how angular momentum is moving within the disk, that motion of those objects may either be inwards or outwards, and that turns out to be quite a sensitive function of the angular momentum transport. But then we're also interested in it for these sort of smaller scale processes that are relevant for early stage planet formation. So one of those is obviously turbulent diffusion. If we imagine that we have this disk of gas with a small admixture of dust, left to its own devices, that dust would tend to settle under gravity to form a very thin layer in the midplane of the gas disk. And that settling will be opposed by any turbulence, which will tend to stir up that dust layer and keep it puffed up. And then radially, that same turbulence could produce mixing, and that's very relevant to observations, particularly in the solar system, where there's a range of observations, some of them by NASA's Stardust mission, which suggests that the particles which we see in the solar system, which we recover, say, from comets, do not have the mineral composition that we would expect if they formed, say, in the outer parts of the solar system. So it seems maybe in the solar system there was a lot of radial mixing of material that was once close to the sun and at some point was then moved to large distances in the disk. And then directly we can be interested in particle concentration. If we want to build planets from initially submicron-sized dust, there's many orders of magnitude in spatial scale that we have to grow through, and so we like to understand the collision rates, the collision velocities, the collision outcomes that occur in a turbulent environment. So these are all effectively independent to some degree reasons we might be interested in turbulence. Of course, they're quite closely related. If we knew the nature of turbulence within the protoplanetary disk, we could hope to calculate these three things consistently, and then an observational constraint on one would give us a fairly direct constraint on what we expect for those other properties. So what's been done about this to date from an observational point of view? Well, let's start with angular momentum transport. And the basic point here, of course, is that if you're in this disk orbiting the sun in Keplerian motion, your specific angular momentum is an increasing function of your distance from the star. So you need either turbulent transport or loss of angular momentum if the gas at large scales is to flow inwards and be accreted. So I'm going to just define here a couple of quantities that I'm going to be using later. Astronomers typically parameterize the strength of turbulent transport in disks in this way. You assume that the turbulent transport behaves something like a scaled up viscosity, which scales with the disk sound speed and the scale height of the disk, which is its vertical scale height, going away from the midplane of the disk. And there's an efficiency parameter here, alpha, which just parameterizes how strong that transport is. So this is a sort of classical way of parameterizing the strength of turbulent transport. We're going to be discussing simulations later, so you can relate this alpha here to properties you can measure in a simulation, the correlation between radial and azimuthal magnetic fields, and similarly the correlation between radial and azimuthal velocity perturbations. Here we have fluid Reynolds stresses, and here we have Maxwell stresses. So that's sort of from the theory point of view. What can you do observationally? Well, observationally, you can try to measure the accretion rate onto the star as a function of the age of the star for a whole bunch of stars in a young cluster. And here's a rather famous example of doing this, one of the early ones by Lee Hartman and collaborators. This is accretion rate in solar masses per year on a logarithmic scale. So these are low accretion rates here, quite high accretion rates here. This is log of the estimated stellar age, and there is a very rough trend that as stars get older, the rate at which gas is piling onto the star goes down. So you can try and ask if you can associate this rough decline in the accretion rate with time with some sort of evolutionary timescale over which the protoplanetary disk is transporting angular momentum. And if you do that, you would estimate that the evolution time of the disk is something like the scale of the disk squared divided by this turbulent viscosity. And then if you know the disk size, say that's 100 AU, you observe that to be 100 AU, and you know that the disk evolves on this observed timescale of a few million years, you can immediately get a constraint on what this viscosity ought to be. And if you do that, you get a number for this alpha parameter, this efficiency, that's about 10 to the minus 2. So at some level, an efficiency of that order is what we have to be aiming for in trying to understand turbulent transport in disks. Now, of course, you can see here that if we hadn't drawn these lines on this plot, you would probably say that there is a decrease, but there is a huge amount of scatter here. So clearly this is a very rough estimate of what might be going on in the disk. Now you can ask whether you can do better by looking at other things that turbulence might be doing within the disk. And one of those is mixing. So you can ask, let's imagine we now take a slice of the disk. Here's the midplane. This would be the surface of the disk, upper and lower surface of the disk. If we have a dust particle within that disk, the vertical component of gravity will be trying to pull it towards the midplane and settle it into a thin layer, while turbulence will tend to be trying to keep it suspended. So you can model that crudely as an advection diffusion equation, where you have a diffusion term in this vertical direction, and then you have some advection, which is representing this gravitational force that is trying to pull the particles into the midplane. So if we could measure the thickness then of a dust layer in a protoplanetary disk, we could compare it with solutions to this kind of equation, modeling based on this sort of equation, and try to get out of that what the diffusion coefficient is for these small dust particles in the turbulence, and backtrack from there to what the angular momentum transport efficiency in the dominant gas component of the disk actually is. So people have tried to do that. Here's one example. And the way you can do that, the way that's possible observationally, is if you imagine you have a very thin dust layer within the gas disk, then that very thin dust layer will, as seen from the star, correspond to a rather small solid angle. So that thin dust layer will not absorb very much of the stellar radiation. If, on the other hand, the dust layer is much thicker and puffier, it will present a larger solid angle as seen from the star. It will absorb more of the stellar starlight, and it will re-radiate that in near and mid-infrared wavelengths. So if you look at a spectral energy distribution of one of these young stars with the disks, this is flux as a function of wavelength, you see there's a photospheric component corresponding to the star, and then there's an excess out between maybe 2 and 10 microns, which corresponds to re-radiated stellar radiation from the dust in the disk. And if the disk is very thin, you would expect that this component is lower, and if the dust disk now is very fat, you would expect more absorption of starlight and re-radiation in the infrared, and this excess here would be higher. So you can model that and try to estimate what the strength of the transport is, and people here who've done that come up with a rather lower number than the estimates based on disk lifetimes, an alpha of about 10 to the minus 4. But this, of course, is quite dependent on what you assume about the size distribution of the dust. It's the very small dust particles that absorb the starlight, but a lot of the mass could be in much larger objects, pebbles or boulders, which observationally you don't see. So there's degeneracy here in trying to take this quite good observation and actually translate it into the quantity you're interested in. Then finally, we can talk about particle concentration, and here again there's quite a lot of theory and at least a little bit of observational evidence. We would certainly be interested if we could get strong local concentration of particles within the gas disk, because that could be a good way of going from very small particles, dust-sized particles, up to the first macroscopic objects in the disk, which we typically call planetesimals. And these are imagined to be maybe 10 or 100 kilometer bodies that you might think of as being sort of analogous to primitive asteroids or comets. And there are popular theories for making planetesimals that involve the collapse of quite large amounts of solid material directly to form those objects, purely under their own self-gravity. And to do that, you require a very large concentration of the solids compared to their average or mean concentration within the disk. So how this occurs is a big open question. The turbulence that could produce that concentration may be purely gas phase turbulence, or it may involve mixed instabilities that involve both the gas and the dust as dynamical players. And this movie that was playing here is just an example of actually a test simulation of some of those instabilities that occur when you have both gas and dust with roughly equal local densities in the disk. Colors here are showing solid densities, and here you can see by the end of the calculation you develop a very filamentary structure of solids with quite large overdensities compared to the uniform distribution of dust that you started with. And this sort of thing may be related or may be testable in some degree with some solar system observations. If you slice open a meteorite, a primitive meteorite, you see these objects called chondrules within the meteorite. Those are maybe 1/10 of a millimeter spheres that were once molten rock, which have solidified in the protoplanetary disk. And if you look at them, you find that maybe 10% of them are actually stuck together with another one of these chondrules. So if you think about that, that says that the density and the collision rates in the environment where those chondrules cooled and solidified were such that there was something like a 10% chance that those objects actually had a physical collision during maybe the 10 or 20 hours which they were cooling from the molten state into the solid state. And you can very easily work out that to get that many collisions actually requires very high overdensities of particles compared to what you'd expect just based on the average gas-to-dust ratio in protoplanetary disks. Okay, so those are the reasons we might be interested in disk turbulence. What do we know about the mechanisms that might actually drive that turbulence? Well, I'm really going to just be discussing one of those, but there are maybe 3 of them which I would say are the focus of much of current research in the area. The one I'm going to be discussing is the magnetorotational instability, which is an instability that occurs in magnetized shear fluids when the angular velocity as a function of distance from the star is a decreasing function. Okay? So clearly in a Keplerian disk, the angular velocity is going as r to the minus 3/2, so it is a declining function. So if that protoplanetary disk is threaded by a weak vertical magnetic field, that will be linearly unstable to this magnetorotational instability. So I'm mostly going to be talking about turbulence that could be driven, initiated, if you like, by this linear process within the disk. But there are other things that could also produce turbulence, and that turbulence could be of quite interesting nature. At sufficiently early times, the gas disk would have been much more massive, we think. It might have had 1/10 the mass of the star, or even several tenths of the mass of the star. And then the gravity of the gas itself shouldn't be ignored in considering the dynamics. So such disks we would describe as self-gravitating, and they develop this characteristic pattern of spiral arms, which is a very non-axisymmetric feature within the disk. And on smaller scales, you might imagine this would also drive turbulence within the fluid at an earlier stage. So we might here be thinking about the first few 100,000 years of stellar evolution rather than the first few million years. And then there's a third possibility, which has received quite a lot of recent attention, which is a radial entropy gradient. Generally, the entropy gradient that we expect to have in the protoplanetary disks will be linearly stable, because the rotation is a strong stabilizing effect on possible, if you like, convective instabilities that would occur in the radial direction. But it is known that there can be a nonlinear instability there, and that can actually give rise to the production of vortices within the disk. Particularly if you start with a disk with the right entropy gradient and put a vortex in there, it can draw on the background entropy gradient and be self-sustaining. So this is an interesting possibility that may be relevant, and vortices, of course, are particularly interesting for the role they might have in concentrating particles. But I'm going to talk just about these first two, and really just about this first one, because I would say this magnetorotational instability and self-gravity together form, if you like, the minimal set of physical processes that we know must be going on in protoplanetary disks. When disks are young, they are certainly massive, so sufficiently early on, self-gravity almost certainly must play a role in the dynamics of those systems. Likewise, they're forming from magnetized molecular cloud cores, so there will be magnetic fields threading those fluids, and therefore they will be unstable to the magnetorotational instability. There may, of course, be other things going on which could be very important. So, I'm going to be discussing this magnetorotational instability, and I first of all just want to give an orientation to the kinds of calculations we do. We've done two kinds of calculations. We do global simulations, so here's an example of that. So the sun would be down here, this would be the midplane of the disk, and here we've tried to model maybe a factor of 10 in radius, and here in this particular case, 1/4 of the total azimuthal extent of the system. So you can do these kind of calculations. These are obviously expensive, and perhaps more to the point, it's quite hard to do controlled experiments in this kind of global environment, because of course what happens here is that as the disk evolves and becomes turbulent, the mass flows inwards and is lost from the computational domain, and that means that the background mean state you're looking at evolves continually over time, and that makes it quite difficult to do nice controlled experiments on the turbulence. So for the most part, we've been instead considering local calculations where conceptually what you do is take a small patch of this protoplanetary disk and simulate it in a local domain with appropriate shearing periodic radial boundary conditions. So you linearize the shear about some point, consider some vertical domain, radial and azimuthal domain. You have periodic boundary conditions in the azimuthal direction. We typically have open boundary conditions in the vertical directions, and then sliding periodic boundary conditions in the radial direction, such that one point on the left-hand side of the domain is at different times identified with a different point on the right-hand side, reflecting the shear in the system. And within this local domain, we solve the MHD equations, and as we'll see, we have to worry not just about the ideal MHD part, but also critically about the non-ideal MHD terms, which are important at low ionization fractions. Yeah, so the seed field would almost certainly come from star formation. So if you took a molecular cloud core, which one of these stars formed from, and just let it collapse, conserving magnetic flux, you would end up, in fact, with a tremendously strong magnetic field in both the star and the disk. So a lot of that field, observationally must be lost as the star and the disk is formed. But what we imagine is that, it goes to a low value but not zero, and so the seed field is coming is coming from the molecular cloud that formed the star and the disk in the first place. So we solve this induction equation, continuity and momentum, of course. The calculations I'm going to be showing are using an isothermal equation of state, which may be sort of roughly appropriate, because these disks are dominantly heated by stellar irradiation. So they're being heated from the top and the bottom, and so their mean vertical thermal structure is going to be close to isothermal. Obviously, we don't consider any radial entropy gradients. We don't consider dissipation in current sheets or anything like that in these calculations. What we do have is vertical gravity. So you see here, this is a density plot, so the stratification between the midplane and the upper layers. As I said, we have open boundaries in the vertical direction. We don't, in these calculations, consider particles. We don't consider dust. And so there's no feedback from particles on the gas, either dynamically or in terms of what they might do for the ionization level within the fluid. Let's see if...
I guess your time is up.
I'll take some questions, yes.
This is a commercial break.
So you post velocity, shear flow velocity at the boundary only?
No, throughout the domain. No, so basically we're working in a coordinate system that has the linearized shear there. So it's a shearing sheet approximation to the dynamics. Okay, so we've been solving these equations with the Athena code. So we've been doing non-ideal MHD with Athena. Just to give a few details of Athena, this is a fixed grid or static mesh refinement code, so there's no adaptive mesh refinement here. We use constrained transport for the magnetic fields. This is a Riemann solver type code. And we use orbital advection, which, coming back to that question, amounts to saying that we take off the dominant shear component and basically solve for the perturbations about that. So the dominant flow is this shear flow, and particularly if you consider a fairly wide radial domain, that shear flow velocity becomes quite large, and if you attempt to represent it explicitly, you end up with large, basically diffusive errors as you're trying to just transport that material, advect that material across the grid. And in the calculations I'm going to be showing, we include ohmic and ambipolar terms. We have some other calculations which are in progress, which also include the Hall effect. But it turns out that in the outer disk, at least, which I'm going to be focusing on today, it seems the Hall effect doesn't have a dominant role. So this is a fairly simple code, and we get quite good scaling with it. This is weak scaling test on the now retired Nix Kraken machine. We get quite good performance there out to large numbers of cores. So let me show you what that looks like. First of all, just in the ideal MHD limits, this is a density rendering here. So this would be the radial direction. This is the azimuthal direction. Here's the vertical direction. And what you see here is that if you start with one of these domains, just initialized with a weak vertical magnetic field, and let it go, it develops into this turbulent state. And what you mostly see here is just density waves bouncing around in the midplane of the disk. Okay. So that's what it looks like in ideal MHD. And so
what is this curve?
This is density, or log density actually. So this is maybe an appropriate simulation if you were thinking about a disk around a black hole or a neutron star where the temperatures are very high. Ideal MHD in those circumstances is a very good approximation to what is going on with the magnetic fields.
The shear is imposed?
Shear is imposed. So nothing can change the background shear profile. So you can ask, well, how well can we do with things like convergence in this kind of calculation? And here's two different aspects you might be worried about. One is, let's imagine we take a fixed domain and simply increase the spatial resolution. Do quantities that we're interested in, such as the rate of angular momentum transport, converge with increased resolution? So this is work by Shane Davis and collaborators from a few years ago. What's being plotted here is basically the angular momentum transport efficiency of the turbulence as a function of time. This is in orbits. And these different colors here are different resolutions. 128 grid zones per scale height is this black curve here. And you can see here the problem in demonstrating convergence in this system, which is that the system is very chaotic and has large excursions in the angular momentum transport rate as a function of time. which occur on quite large timescales, right? The natural timescale here is the dynamical timescale, which is 1 orbit or 1 over 2 pi orbits or something like that. Here we're looking at 300 orbits, and you see these long timescale variations in the stress that are occurring. So the limitation here in studying convergence is principally that obviously you would need to run these calculations for exceptionally long periods simply to smooth out the statistical noise. However, these people at least claimed that at this 128 zones per grid point, perhaps they were approaching some convergence with the spatial resolution. Now, there's then a second aspect you might worry about, which is the size of the domain. If you make one of these local domains larger, do you actually get convergence as the domain size gets larger? And that's something we've looked at. This is domain size here. Again, these points here are different measures of the angular momentum transport efficiency. And this is actually a bit better story. Here, unless you have very small domain sizes, which are not plotted, here actually you do seem to get reasonably good convergence as the domains get larger, at least in ideal MHD. Turns out with ambipolar diffusion, which tends to smooth out small scales, you actually need rather larger domains to make the same statement. And the angular momentum transport efficiency you get from these calculations, you can see it's about 0.01 in both of these cases, is actually quite consistent with what we get from the global calculations we've done. Of course, those make a trade-off that they don't have such good small-scale resolution.
Go back to the right-hand picture. So what are the other?
The other things are just different measures of different. I'm trying to remember exactly what we've got here. I think it's like the ratio of magnetic field components, which is related also to the stress level. So if we, again, just for the moment think about ideal MHD, one of the interesting things we see even in ideal MHD is that there's some sort of intermediate or large-scale structure which develops from the turbulent flow. And this is the part of it that's best known. So what you're looking at here is toroidal magnetic field averaged radially and azimuthally over the domain. So the one spatial variable left is height, and it's being plotted here in a space-time diagram. So this is not R, this should be Z. So this is height above the midplane in scale heights, plotted as a function of time. And the blue and yellow colors represent toroidal field of opposite sign. So what you see here is periodic reversals in the magnetic field in the midplane of the disk, or in the simulation box. That field is forming, it then escapes buoyantly out of the surface of the disk, and it's replaced with field of the opposite sign, and that has this actually extremely periodic behavior. So these two different plots here are different size domains. What we found is as you go to larger and larger domains, actually this periodic reversal, this sort of butterfly diagram type thing, just becomes more and more smooth and periodic.
The strongest fields are some mid-heights?
The strongest fields compared to the gas pressure are at mid-heights, yes. Absolutely, they're strongest at the midplane, typically. So this property, this property of the magnetic fields having some periodic behavior, doesn't have any immediate implication we know of for planet formation. There's another kind of large-scale or intermediate-scale structure that perhaps does have an implication for planet formation. Here we're looking at the radial dependence of the density, now averaged azimuthally and over height. And again, it's a space-time diagram. So this is density, and this is perturbations from the mean. And what you see here is that over time, the disk develops a kind of zonal flow in which there are low density and high density regions which sort of sit alternate to one another within the disk. And these are basically equilibrium structures or quasi-equilibrium structures. They last for hundreds of dynamical times. And obviously there's a pressure gradient here set up by this density perturbation, which is balanced by a variation in the azimuthal velocity around the star. So they're in basically an equilibrium state. And this could be important because if this, say, is a pressure maximum, particles, dust particles, would tend to flow towards that pressure maximum and accumulate there, and those could be good sites for forming planetesimals. So we're sort of interested in this and working on this. A problem with this is that whereas this magnetic field behavior appears to be very universal, it appears to not depend on domain size, you see it in local and in global calculations, here, there is some tendency for these zonal flows to expand to basically box-filling dimensions. So clearly, the local approximation is sort of breaking down there. The power is going to large scales, and it's unclear, what would really happen in the physical system. Okay, so that was ideal MHD. What happens when we start thinking about the non-ideal MHD terms? And the key point here is that in the protoplanetary disk, the ionization level is very low, and unless you're really close to the star, so maybe close enough that the temperature is about 800 Kelvin or above, 800 Kelvin is where the alkali metals start becoming ionized, the dominant source of ionization is always non-thermal. Okay? The thermal ionization level is really vanishingly low. So the sources of non-thermal ionization maybe 3 or 4. One is radioactive decay of short-lived isotopes that would maybe be present in the disk, having been formed in nearby supernovae. Aluminum-26 is the dominant one of those. Another thing would be cosmic rays. Another is stellar X-rays, because these young stars are quite luminous sources of X-ray radiation. So what's plotted here is column density from the top of the disk downwards into the interior, and an estimate of the ionization rate that would be being produced by those different sources. And if you imagine that the surface density at 1 AU might be 1,000 grams per square centimeter or 10,000 grams per square centimeter, you can see that all of these external ionizing sources will have been attenuated by many exponential stopping lengths by the time you reach the midplane. Near the surface, stellar X-rays are almost certainly the dominant source of ionization, unless you go very far out in the disk, where there could be a thin layer where far UV photons also produce reasonably high ionization levels. So because of this, we have low ionization levels, we have quite weak coupling between the gas and the magnetic field, and we have a dominant role of these non-ideal MHD terms. So we can at least qualitatively see how that might work by just considering the induction term here and the ohmic diffusion term here. So if we did a calculation with just the inductive term here, we would be in this ideal MHD regime where we have linear instability of weak fields with a particular growth time. And so if we consider a scale h, that growth time is of order that scale divided by the Alfvén speed for the magnetic field we're considering. So that would be the linear growth time for a initially non-turbulent disk threaded by a weak vertical magnetic field. Now, if on the other hand we just considered this ohmic damping term, that would obviously give us a damping time scale, which on this same scale would be something like the square of that scale divided by the resistivity. So we can obviously equate those two and ask, how large does the resistivity have to be such that we would expect this ohmic term to strongly damp the instabilities that would be present in ideal MHD? And that gives us a critical resistivity, which can just be written in this simple form. So Gamy, now almost 20 years ago, made this kind of argument and showed that in the inner disk, so if we consider certainly the terrestrial planet-forming region, the resistivity we expect based on the non-thermal ionization should easily be high enough to damp MHD turbulence near the midplane. So near the midplane, where the non-thermal ionizing sources can't penetrate, the resistivity will be high enough to really wipe out any MHD processes going on there. So here's a movie showing that. So this is with some particular profile of resistivity. It's not so exciting as the previous one because there's much less going on. This is actually magnetic fields you're looking at here. The sort of structure you expect is that near the midplane, everything is really very quiescent. There's really very little going on there. There's maybe some magnetic fields, but they're not turbulent. And the only place where you have turbulent activity is in the surface of the disk, where the ionization fraction is relatively high. So you have a sort of layered structure with a quiescent midplane and all the activity taking place in the surface layers that's normally described here as a dead zone. So that's a simulation. Here's a cartoon of what it might look like. Here's the star with its X-rays, which are ionizing the surface of the disk. If we're really close to the star, we're hot enough that we're thermally ionized, and we have a nice turbulent disk. If we go further out, the midplane has this dead structure. The activity is taking place in the surface. And then if we go far enough out, the X-rays and maybe the cosmic rays will provide at least a low level of ionization throughout the whole disk, but we have to worry about ambipolar diffusion because in those very low density regions, the ions and the neutrals, which are being coupled by collisions, are not being coupled that well. So what we've been interested in particularly recently is to look at this outer part of the disk. What happens in this outer region where ambipolar diffusion takes over from ohmic diffusion as one of the dominant non-ideal terms. The Hall effect is actually also still important on those scales. So the first thing we can do is to consider, in just an idealized model way, how does ambipolar diffusion affect the strength of turbulence in this kind of environment. So this calculation here is a very simple one, where what we do is ignore, in fact, the vertical stratification of the disk, and just consider a box of fluid with shear, no vertical stratification, and some initially imposed magnetic field. And you can characterize the strength of the ambipolar diffusion via this control parameter. Gamma here is the collision rate between ions and neutrals. This is the ion density. This is the angular velocity. And this corresponds to the number of ion-neutral collisions that happen per orbit. So if we plot the strength of angular momentum transport now as a function of this control parameter, what you see is that for large values of this parameter, you sort of approach a plateau, which is rather similar to the values you get in ideal MHD, or in fact identical to the values you get in ideal MHD. But then there's this rollover towards low values of this parameter, and for the lowest values, we can only actually measure an upper limit on the turbulence strength. It basically just decays away as the calculations continue. So these are idealized calculations. Of course, in reality, the ion density, so at one radius, the angular velocity is fixed, but at one radius, the ion density varies with height, and then the collision rate between ions and neutrals, that also varies with height. And to determine those things, you need quite a complicated chemical model of the disk that will say what the ionization fraction is at each different level within the structure. So we've been using a model that's basically the same as one developed by Perez-Becker and Chang. And this is a model where in the outer part of the disk, the most important ionizing source is actually far UV photons from the star, which ionize things like carbon in the upper layers of the disk. Now, FUV photons don't penetrate very far into the disk, so all they ionize is a very thin layer, maybe a hundredth or a tenth of a gram per square centimeter on the surface of the disk, really a skin. But if you do that and you calculate what this ambipolar control parameter is as a function of height, you get something that looks like this. You get sort of ideal MHD conditions in these thin surface layers, and then actually quite strong ambipolar damping in the midplane of the disk. So based on that, what we would sort of expect, based on those previous calculations I showed you and what we actually find, is that if there's nothing else going on here, most of the mass is in this region that is strongly damped. There's not much mass in the surface layers, and the predicted level of turbulence is really rather weak. And that's too weak to explain gas flowing into the star at the measured rate and to allow the gas disk to disperse in the sort of times we see. Here's just a plot of that. So this is now height, again as a function of time. Here you're looking at magnetic stress and fluid stress. Here you can see these magnetically active surface regions, and basically nothing at all going on in the midplane. This is a model appropriate for 100 AU away from the star. You can see there's still some waves penetrating to the midplane, a little bit of fluid stress being produced there. So that's not really very satisfactory, because that really suggests that a protoplanetary disk shouldn't be an accretion disk. Okay? The protoplanetary disk would just sit there and actually do nothing, right? It would just sit there in principle forever, right? It wouldn't accrete. If there was no reason to blow it away, the gas would really not go anywhere. And that's contrary, of course, to what we observe, because we do observe gas accreting onto the star. But there's a possibility here for producing some accretion. We can take that same disk model and add a larger vertical field to the disk. Okay? And that vertical field, as I was saying, might come from the star formation environment the disk formed from. And interestingly, what we see is that when we vary that vertical field parameter, we get sort of qualitative changes in the sort of solution we get for what's going on in the outer disk. So what we have here are three different vertical field strengths. This lowest one is a very weak vertical field, parameterized by this beta Z parameter, which is the ratio of the thermal pressure to the magnetic pressure in the midplane, corresponding to the vertical field component that is imposed. And here you see we talk about a very weak vertical field, because this beta parameter is 10 to the 5. And here we have this situation where nothing is going on in the midplane. The only activity is taking place in the surface layers. However, if we then increase the magnetic field strength, as parameterized by this, to 10 to the 4, here we still have these active surface layers, but now we have some more action taking place in the midplane of the disk. And if we make things even stronger, we get actually something that looks completely different. This sort of activity, these periodic reversals go away. Here we get actually quite large-scale fields. The disk is not really turbulent, but there is a laminar stress within the disk, and also actually a stress from material leaving the domain and exerting a stress on the disk surface. And these two panels here have enough stress to explain the sorts of accretion rates we see in young stars.
Are you maintaining that vertical field at the boundary
The vertical field, yeah, it's conserved. It can't go anywhere. Okay, so with enough vertical field, you can get these high enough accretion rates, and that's what's just shown here. Here's stress as a function of height on this upper panel for different values of these vertical field parameters. So blue is this lowest vertical field, red is the highest one. But an interesting property is that a substantial component in those calculations, a substantial component of the stress, is actually non-turbulent. Okay, so it's quite different from what we see in ideal MHD. And the upper layers of the disk end up being magnetically dominated. So the magnetic field is the strongest pressure in the upper parts. Now, there's also an interesting possibility, which is still quite speculative, I should say, of a transition between turbulence within the disk and a wind from the disk. So we have these sort of two possible ways in which angular momentum could be transported or lost within the fluid. It could be mixed by turbulence radially, or it could be simply lost in a magnetically dominated wind from the surface of the disk. And what we see, these are renderings of field lines here. If we have weak vertical fields, we have these rather tangled, primarily toroidal fields, which are turbulent. If we have stronger vertical fields, you can see we get a much more organized field structure that looks much more like a magnetic wind coming from the system. So at face value, I would say, wind angular momentum stress dominates over turbulent transport for sufficiently strong mean fields. And this was also found by other people, Juning Bai and Jim Stone, found this occurred at smaller scales in protoplanetary disks, where ohmic diffusion rather than ambipolar diffusion is the main thing going on in the midplane. What I should also say is that these local simulations are a really, really bad way to try to study winds, because you can never put the boundary conditions far enough away that they are clearly negligible. So at best, this is just sort of a suggestive idea of what might be happening. Really, you need to do global calculations to say whether this is correct.
So those were field lines, right? But you talked about vertical field?
Yes, but the vertical field is still here. You see, still here is actually still weak. Okay.
Okay, so it's just that it's stretched out so much on the shear.
Yeah. So the dominant field component is always the toroidal component, because the shear is producing fields by shear is by far the most efficient thing you can do. Okay, so let me finish now with just a few minutes about observational tests. And I mentioned a few observational tests based on disk lifetimes and the thickness of dust layers and so forth. Those are things that have been done. Obviously, those are quite indirect ways to get at what the turbulence is doing. There are both theoretical issues in the interpretation, and there are observational issues in for example, dealing with the scatter that is present in young systems. Now, a better thing, clearly, would be if we could measure the turbulent velocity directly by looking for the broadening of spectral lines, which we can observe from the disk. And we can make a simple estimate of how strong those might be. Let's imagine we have an annulus of the disk in Keplerian rotation, and we observe that at some inclination angle I. Well, the Keplerian velocity, which is obviously going to be the largest thing we see, is going to be that Keplerian velocity times the sine of the inclination of the system to the line of sight. Now, there will also be thermal broadening, which will depend on the sound speed, and the sound speed is the thickness of the disk divided by the radius times this Keplerian velocity from the requirement that the disk be in hydrostatic equilibrium. So typical protoplanetary disks have this parameter of maybe 0.05 or 0.1. So the thermal broadening is going to be, depending on the inclination angle, maybe a factor of 10 or 20 less than the Keplerian velocity. Obviously, the situation will be a bit better if the disk is really face-on, and so we suppress the Keplerian component. Now, the turbulent velocity broadening to order of magnitude is going to be something like alpha to the half times this sound speed. Okay? So then we pick up this factor of alpha to the half, and we think alpha, we said, is maybe 10 to the minus 2. So this is going to be, again, about a factor of 10 down from the thermal broadening. So what does this mean? This means if we can measure molecular lines coming from the disk, and we certainly can measure molecular lines coming from the disk, and if we can model the thermal structure and the velocity structure at a sufficiently precise level, then we could hope to measure the excess broadening that is caused by this turbulent component over the thermal component. But clearly this requires quite good observations and quite good modeling, because the effect we're interested in is very subdominant to the Keplerian velocity, and it's also subdominant to the thermal broadening. But this has been attempted So this is work by Meredith Hughes from now several years ago, not with ALMA. This is with a small millimeter array, which is an older sub-millimeter telescope. And what you're seeing at the top here is the line profile observed for a particular transition. This is CO 3-2 from this particular disk system. And this is velocity units here. This is the flux in the line. And the histogram here, the black histogram, is the actual data. And these other curves here are theoretical models which are plotted over that. And the only point I'd like to make from this is that, as you can see, the velocity channels here in these millimeter observations have very high resolution compared to the expected width of these lines. And, you know, if you can beat down the noise here and get a nice smooth curve, there's clearly a possibility of measuring this to very high levels of precision. And indeed, Hughes and collaborators looked at this for two systems, and for TW higher, that almost face-on disk I showed right at the start, they did not make a measurement, but they did obtain a limit, which was at the level of 1/10 of the sound speed. And that, remember, is the level at which we expect to see these turbulent signals in the line shape. For this particular system, which is a different system, this is a more massive star, they actually made a 3 sigma measurement that was above this level, about 40% of the sound speed. However, as you can see from here, with this SMA observations, there are unmodeled systematic things, particularly here, which might give you some pause for concern about that observation. So we've been interested in following up on this, both on the theory side and on the observational side. And on the theory side, what we're doing is making detailed predictions for these turbulent velocities and line profiles for the specific systems that are the best candidates. So there are only a small number of disks that are, both close enough to us, large enough, face-on enough, that these measurements we think can plausibly be made. So what we've been doing is doing numerical simulations tailored to the specific parameters of those systems, the density the disks would have at different radii, which has actually been measured in most cases, and then estimates for what we think the ionization structure ought to be. And these are some examples of the kind of things we're coming out with. These are measurements of the broadening component, the turbulent broadening component as a function of the sound speed, as a function of height for different models. Typically what we see, of course, is that near the midplane, the turbulent velocities are rather low. But as you go towards the surface, the activity there is stirring up the disk, and actually near the surface, we get values that are typically between 1/10 of the sound speed and the sound speed itself. So that measurement I mentioned before, suggesting a turbulent velocity of 40% of the sound speed, CO 3-2 transition is quite optically thick, so that is coming from the surface of the disk, and that would actually be consistent with these expectations we would have based on MHD models. So we've been calculating these velocity profiles, how strong the turbulence should be at different radii and different heights, and then using a radiative transfer code to actually calculate what line shapes you would get out of that for particular transitions. So the idea here then is that observationally, you look at a variety of different transitions, some which are very optically thick and which come from the surface of the disk, some which are more optically thin and come from nearer the midplane, and hopefully you can see that those near the surface have high velocities, and then as you go to the midplane, they have lower velocities, and eventually you reach a plateau. And if you could do that, then obviously that would give you some confidence that these kind of structures that we're seeing in the simulations perhaps exist in real systems. So we're proceeding with that. We have some approved Cycle 2 ALMA program, which Meredith Hughes is leading, to observe one of these large nearby disks, actually in multiple molecular transitions. We believe both the spatial resolution and the signal to noise should be sufficient to make a number of measurements along these curves. So I'll finish off there with a summary. I think we've made some progress in simulating turbulence in these disk systems. The non-ideal MHD is certainly critical. We believe net magnetic fields are also critical, and that is sort of both interesting and maybe problematic because it says that the relic magnetic fields left over from star formation play a long-term role in determining what happens to protoplanetary disks thereafter. And I believe there are excellent prospects for at least, obviously not really direct observations of turbulence in disks, but at least more direct observations of turbulence through sub-millimeter observations. Thank you.
For Phil? I have a question. In your simulation, you kind of specify a shear, and also you have certain scale, the radial scale. So that kind of predetermines the velocity scale in your calculation. And is that consistent with the other velocity scale, which is the acoustic velocity used for various estimations? Are those two kind of consistent?
Yeah, so there's sort of two questions here, or two issues here. One is that if you do these kind of shearing sheet calculations with no vertical stratification, right, then indeed there's some degeneracy there in the problem. Okay, and indeed what's found is that in some unstratified calculations there is really no convergence at all, and as you go to higher and higher resolution, actually the stress just gets weaker and weaker and weaker. Okay? So it appears that having the vertical stratification, which really sets a physical scale based on the sound speed, having that vertical stratification turns out to be very important. And so there's a very strong difference in the convergence properties of the stratified calculations and the unstratified ones. And that's actually why we're really focusing now on the stratified limit, because the unstratified limit, I think, has some sort of some interesting mathematical properties, but it seems to be quite divorced from what's really happening in the disk.
I have two questions. One is, what is the typical field strength that you're imposing in the vertical magnetic field from the surrounding cosmos?
It's of the order of 10 milligauss or something like tens of milligauss.
And on this particular subject, have the more global simulations had something to say? Because you've shown us things that are the local sharing boxes.
So not really with the non-ideal MHD. So there are some calculations which do include ohmic diffusion, which are global. And the main new thing you might get there is you might get very interesting radial structure, say where the ionization state changes over a short radial length scale. For the moment, I would say the ambipolar calculations are still quite expensive to do with the right level of ambipolar diffusion, and so it's quite difficult to do those globally at the moment, and the Hall effect even more so.
How much extra computational resources does that take?
It's about a factor of 10.
10?
Because where the density is very low, the explicit ambipolar timescale is very short, and the way we're doing it, we're limited by that.
Since the big picture here is to try to understand the formation of planetary systems, I wonder if the diversity of planetary systems discovered by Kepler and their size distribution and distance distribution of their orbits can provide any useful constraints on this sort of early stage.
Yeah, so I think obviously the big question with Kepler systems is that they're all close in and they contain quite massive planets. The big puzzle to my mind there is that the migration times are extremely short. So I think in general terms that says something about how interaction of maybe Earth mass or a few Earth mass objects with the gas disk has to proceed, and there clearly has to be some way to prevent those just migrating into the star. So having a modest level of turbulence at the midplane is the best situation for preventing them migrating extremely rapidly, because that affects how they interact with co-orbital material. But actually going from there to really saying something about the architecture of those Kepler systems, I think is still quite a distant hope.
I think one of the surprises from Kepler are how common these very compact systems with low mass planets, like systems of planets inside the orbit of Mercury in our own solar system, that are exceptionally flat, and I would think that those sorts of systems might be able to offer some useful input.
Yeah.
If I could try another question, you showed us some large voids and structures that appeared. Do you understand how these come about, and are they responsible for these sort of major excursions that you were seeing in the transport rates?
I would say, you know, there are some tentative models. I mean, you know, basically sort of talk about mean field type models, which, you know, give some insight perhaps into what is going on. Certainly, it appears that the Lorentz force is critical to producing those. They really are MHD phenomena. The variability, I would say, is particularly poorly understood. And so one interesting thing we actually found is that, you know, as you go to larger and larger domains, some quantities converge very nicely. Actually, the variability does not converge nicely. And actually, as you go to larger domains, the variability goes down faster than you would expect, just based on the statistical averaging of, you know, the domain size. So somehow the large-scale magnetic field is sort of interacting with the fluid to give you unexpected behavior, and we don't have any understanding actually of why that should take place.
Thank you. If no more questions, let's thank Phil again. Thank you.